Rigid body statics. Okay. And the one at A has thrust. All right, so free body diagram. um, Okay, so there's the body that we're going to isolate. It doesn't say anything about mass, I would guess. Okay, so let's see. We have this force from the cable down. The thrust is at A. If you have a pair of these, almost always one of them provides thrust. It doesn't tell us a coordinate system, so I'll go at, I'll call this RAX, RAY, RAZ. Over here, you just have RBX and RBY. And then 600 and 750. One, two, three, four, five. 1, 2, 3, 4, 5. Okay, so that should be it. And our about point, I guess I'll choose it over here. So for the row vector, we have 0. For the force vector, RAX, RAY, I'm not going to make it through today. Jesus fucking Christ. I'm going to edit that out. Okay. Okay. 0 row vector, force vector is RAX, RAY, RAZ. Moment is 0. I think in 25 seconds this is going to crash, and then I'll have to restart it if the pattern holds. Then the cable force. Okay, what's the row vector to the cable force? I did not. We have to know those dimensions. It's in millimeters. Okay. Okay, 200, 200, positive 200x, wait, 1, 2, okay. Positive 200x, negative 200z, the way I have it. Okay, so positive 200x, 0y, negative 200z. And the force vector, that is in the negative y, so that's 0, negative t, 0. And now the cross product is negative 200t for x, 0 for y, and negative 200t for z. And then the 600 and 750. So that is, was it another 250 in the z direction, negative z direction? Is that what it said? And then a 200y. So, okay, we have just positive 200y and then 450 for negative z, is that right? I'm just trying to remember what the dimensions were. 200, yeah, 450 in the negative z. And then we have 750 in the negative x, 600 in the negative z. So these are going to be pretty big numbers. Okay. Okay. Oh, okay. Yeah. Well, let's just finish this table and then I won't go through the whole calculations, but so 200. Okay, so we got negative 750, 0, negative 600. Is that what I said? Yeah. So what's 200 times negative 600? 12. So 12 times 10 to the 4. So, yeah. So negative 120,000. And then 450 times 750. $337,500. Okay. And that is positive. And then 200 times 750 must be 150,000. And that is positive. And then the last one is our B. So that's probably 650 in the negative z. And nothing else. We have an RBX and an RBY, but no RBZ. So we got positive 650 RBY. Negative 650 RBX and 0. Okay, so let's see what equations we should have. We have, for forces, we have an x. You know, I'm just looking for if there's any equations that just say 0 equals 0. We have stuff in the x equation, stuff in the y equation, stuff in the z equation. Then for moments, x, y, z. So we have non-trivial equations for all 6 of these component equations. And for variables, we need 6 variables. We have 3 there, 4, 5, 6. So it should hopefully work.
Isn't one of the equations negative 200t equals 0?
Negative 200t, no. It says negative 200t plus 650 RB is equal to negative 120,000.
I think he's talking about the Z. But that's
the Z. Oh.
That has
Okay.
150,000.
Yeah. Okay. Any other questions on that one? Any other problems you'd like me to go through? 15, yeah. Okay. All right, so free bodies, something like that. The gear on the right, blah, blah, blah. Okay, it doesn't say, usually it says something about thrust. It doesn't mention anything about thrust in this problem at all for either of those two coaxial joints. Is there a problem with that? Normally, I mean, normally there would be, but notice there are no external forces that are that are acting along the axis. Okay, and so that equation is just going to come out to say 0 equals 0. If one of those we had said there was thrust in it, it would have just come out to say RAZ or whatever is equal to 0. Okay, so it really doesn't affect the problem, although usually you do see it. Okay, so over here we have a force component that way and that way. I'll call that RCZ, and I'll call this RCY. Then we have 96 pounds there and 265 there. At D, we have R, D, Z, and R, D, Y. And then uh, 530 and 192. And I'll put my about point here. If you've already done these problems, be sure you just check your approach against this. It's a good way to catch mistakes if you made a mistake somewhere. If, you know, I mean, dumb mistakes are no problem, but it's a good way to catch things you're misunderstanding if you did something wrong at one step. Okay, so first RC, we got 0, 0, 0. The force vector is 0, RCY, RCZ, and the cross product is 0. Then so the positive x in this coordinate system goes to our right. So the place where these two forces act is at 4 inches in the positive x, and then the radius of that gear is 1.5. So 4 in the positive x, 1.5 in the positive y. And since those two forces are acting at the same spot, we can think of it as a single force. You can always do that just to save a little writing or whatever. So we have 0 in the x direction, negative 96 in the y direction, 265 in the z direction. So 0, negative 96, 265. What's 1.5 times 265? 397.5 for x. For y, we have, what's 4 times 265?
4 times 265?
265.
Negative 1060.
Negative 1060. And then 4 times 96?
Minus 384.
Minus 384. Okay. And now we're to RD. You just have a y and a z. The row vector is 7 in the positive x. Uh, 0, RDY, RDZ. And so you get 0. negative 7 RDZ and positive 7 RDY. And then the last force, so that is 9 in the positive X and 0.5 in the positive Z. Again, I'm going to treat this as a single force vector because it's all at a single point. So that is 530 positive Y, negative 192 Z. So that's 0 for X. Did I write that down right? So 0 for X. What's 9 times 192?
1720.
Okay. So that's positive 1720, you said?
28.
28.
Guy,
Yeah.
how is it 0 for X there?
0 for X. It's not.
That's what I'm about.
Okay. Thank you.
That's where I went wrong.
No, okay. So 0.5 times 530. That's 265
Yeah.
And then
negative. And then 9 times 530.
4770.
4770.
It's like when you set up your moment equation for X, it doesn't seem to make sense.
Yes.
That's
Does
where
it say something equal?
Right. Okay. So it doesn't make sense. And this is the one problem that you have like this. Okay. So look at this thing. I mean, look at what's happening to it. Just look at the 530 force and the 265. Okay. Those are both, well, I guess they're going opposite directions, but they're both trying to turn that thing, right? So you could see if those moments offset. I guess we already calculated whether they do, and they don't, right? And so there's going to be a net moment turning that thing, and there are no reactions keeping it from turning, okay? So it's going to have angular acceleration about that axis. And so the answer is, we're taking into account the stuff that is static, and the stuff that isn't static, we're ignoring it. Okay? So there are two things we're ignoring. The first is that there's the X force equation. That's the one that would involve thrust, is 0 equals 0. So that doesn't help us. And the second one is the moment about the x-axis is not equal to 0. Okay, so now we have, well, let's count variables. 1, 2, 3, 4. So we have 4 variables, 4 equations, and you can solve for those loads. So yeah, if you just think like static equilibrium, this isn't going to work. The key thing is that it's static in a lot of ways, but it is going to spin about that axis.
My instinct was to ignore
Yeah.
the X.
that's like because when I thought about it, I was like, this thing is
But
turning.
I was just like, I don't know if I can.
Yeah, I should maybe give a little better hints on that one than no hints at all. But yeah, that's the idea, and I just wanted to see one like that, where like, yeah, there are cases where it's not static everywhere, but you can still use statics to figure out the stuff you want.
Ignore the something equal to 0.
That's right. And the key thing is there are no loads that depend on like what kind of angular acceleration it has about its axis. And so it just doesn't matter to us.
Yeah.
So
Okay.
what we're looking at really is how much those bearings are resisting the 192 and the 96.
Well, actually, since we're also looking at how they resist the two that are creating the moments. You know, those are producing reactions there too. You could, look in there and figure out what it is. The only way that they wouldn't affect the reactions is if they were a couple, but they're not. Any other homework problems you'd like to see? That is the weirdest one, and I mean, yeah. It probably would be a good idea to just put some hint in there, like, look, it's not going to be perfectly in static equilibrium, but
In that case, if we
Yeah.
have a problem like that, should we like write down our thinking on like this is not in static equilibrium because of this force, or can you just write it off? Or just,
yeah.
let me just do the calculation.
Okay, so I will not ever give you an exam question like that. I just wanted you to see one of them. But there are also cases when you get to dynamics, if we get far enough at the end of the class, you'll see some that look like that, but because of asymmetries in the moments of inertia, you actually won't be able to cancel those out, and the moment that you're applying about the axis actually does affect. So it's not super easy to see until you go to the equations and you see that all you have those those moments doing is creating a moment about the axis. That's all they're doing, and so you can just throw that out. Okay, so the next topic is centroids. And we're going to use centroids for a couple of things. Think of the centroid as the geometric center of an object. And you can have centroids in 2 or 3D. If the object is homogeneous, and by homogeneous I mean like
Uniform density.
yeah, just a uniform material the whole way through. So think sugar cookie, not chocolate chip cookie. Then the centroid is the center of mass of the object. We'll use centroids for 2 things in this class. The first is to find an object's center of mass, and we'll use that to figure out where the weight is applied. So far, all the objects we've dealt with have been very symmetrical shapes, and so you can just kind of eyeball where the middle is, rectangular shapes and stuff. Well, when we get to less regular shapes, you'll have to calculate where that weight force acts. Okay? And the second thing we'll use it for is for distributed loads. And a distributed load is, in this class, I mean, it's a force that's spread out over some area or some distance. In this class, we'll do it in 2D, so it'll be spread out over a distance. In fact, really, these are the same two things, because the force that gravity applies to an object is a distributed load. It doesn't calculate where the object's center of mass is and then apply a force vector. It applies a little bit of force everywhere, and then the effect, actually it's an equipolant system like we talked about last time. You can, if you're treating this thing as a rigid body, it behaves exactly the same if you apply it as a single force vector at the center of mass. Okay, but really it's applying a little infinitesimal force to every infinitesimal piece of volume or area. Okay, so the centroid is defined by an integral. And I'm going to give you that formula, and I'm going to do one example. But basically, then you're done dealing with these as integrals. And I'm just trying to show you why you don't have to do these integrals over and over again. But this is the definition of the centroid. So the integral definition of the centroid. If you're in 2 dimensions, it's an area definition. And you always denote the centroid as X bar, Y bar, or I mean, just the over bar says you're talking about the centroid. And the definition is 1 over the total area times the integral over the entire area of X, Y times dA. So this dA is your infinitesimal area. This is the centroid of your infinitesimal area. So that's the centroid of whatever you're choosing as your dA. And I think probably having done Calc 2, you haven't done a ton of this kind of integral yet. With integral definitions like this, when you do have to use them, which doesn't tend to be very often, but really the key to it comes down to making a smart choice about how you're going to divide this up into infinitesimal area dA. You know, in 3D, it's similar. Okay, tell me what you think changes here. So we're definitely going to go X bar, Y bar, Z bar. And it's equal to 1 over volume, good, times the integral over the whole volume of X, Y, Z, dV. Perfect. So this is an example. Most of my examples are like showing you, let me call this something else actually. Let me call this a derivation for a right triangle. Okay, so it would be a real bummer if every single time you got to a new shape, you had to figure out how to use this integral definition. you know, but I'm going to hopefully show you why you don't have to do that. Okay. So we're going to go, this is going to be our shape, this right triangle. And I'm going to call the length here B. And I'm going to call this H. And I'm going to divide this up into, well, let me show you a coordinate system first. Okay, so I'm going to do this all in this coordinate system. Okay, and my infinitesimal areas are going to be like the ones that you use when you're defining the integral itself, you know. So this, for this infinitesimal area, we're going to go out some distance x. The centroid of this piece, using the center of mass thing, is going to be half of the height of the top, right? If this is if the height of the top is y, this is y over 2. Okay. So how are we going to calculate the height of that rectangle for a given x? Notice that the top of every single rectangle falls along this line, right? So we just have to come up with a formula for that line, an equation for that line. So what's the equation for this line? If you use mx plus b, there's no y-intercept, because this...
H over B.
Yep, that's right. So y is equal to h over b times x. And so our y over 2 is, bless you, h over 2b times x. And our dA, well, the thickness of this thing, we're going to call dx. So we're re-expressing all this in terms of the variable x so we can integrate it. Okay, so our dA is going to be it's going to be the height of the whole rectangle times dx. So that is going to be, the height is h over bx times dx. xy, this is the centroid of our infinitesimal area dA. Is going to be x for the x component, and for the y component, it's going to be h over 2b times x. And now we're just putting this whole thing together. Anybody have any questions about any of these things I've done here? You don't really have to understand that. Like, really what you need to have is kind of a big picture. Just remember that if you're careful about your dA, you can go through, re-express this in terms of variables, and then calculate this. So x bar y bar is equal to 1 over the total area. The total area of a right triangle is h times b over 2. So this is going to be 2 over, call it bh. times the integral of the vector x, h over 2b x, times dA, which is h over b x dx. And since this is all in terms of our variable x, what are the bounds of our integration going to be?
0 to b.
0 to b, perfect. All right, well, I'm going to simplify this a little. We got the 2 over bh outside. The integral, we have, for the x component, hx squared over b. For the y component, we have h squared over 2b squared, x squared, and then we're multiplying it by dx.
Wouldn't you just take out hb to the outside of the integral?
Yeah, you're right. That would have been quicker. Let's do that now. Okay, what do we have here that we can cancel? We can cancel 1h there with 1h in each of those. And then we can pull out 1b. So we have 2 over b squared times the integral x squared and then x squared over 2b. Does that look right?
hx squared over b.
H, yes, thank you. So we got 2 over b squared. And then our integral, we have x to the third over 3, h x to the third over 6b. Evaluated from 0 to b. And so we get 2 over b squared times b cubed over 3 and h b cubed over 6b. And that is 2b over 3 squared, and h over 3. Okay, so what does this say? A right triangle, if our centroid is like here, the distance from this end, from the pointy end in the x direction is 2b over 3, which means this is b over 3. And this is h over 3. Okay. But now the point of doing this is we don't want to have to do this every time we have a right triangle. We never have to use that integral again for a right triangle. all you have to do is use this formula that we just derived. Okay, so now anytime you have a right triangle and you want to know where the centroid is, you just go a third from the wall side in each dimension, you know, and you're there. And so this integral definition has to be used once. The first time somebody in the whole world wants the centroid of that shape, and never has to be used again. Okay. Since people have already done this for any shape you can imagine, so since people have already done every shape, we'll just use formulas for centroids from now on, and you won't have to do this. Okay, so I'm going to give you a chart of all the algebraic formulas for all the different shapes, and then you'll use that. Yep.
Just from my curiosity, when you're, like, if we ever have to calculate the integral.
Yeah.
How did you do that with like the X and Y? Do you just do it two separate ones basically and then put it back together at the end, or?
Oh, yeah. How do you integrate a vector like that?
Yeah.
Yeah. They're totally independent of each other. So you just think of them as two separate,
Two separate ones.
yeah, two separate problems. Exactly. And that'll come up in dynamics and deform a lot, actually. Yeah, I sort of glossed over that. But you can think of X, calculating the centroid, you're calculating the X centroid, and then separately calculating the Y centroid. Okay, any other questions? Okay, that is all. And I will give you the weekly assignment today, because I guess we still won't have a daily assignment.